Okie dokie. So, welcome back, everybody. So we have now been introduced to the basic groups of chemicals that we could be encountering here in this course. So now we're going to begin two lectures where we think about how those chemicals might be introduced to the environment and some things that we want to consider as they are moving through and circulating through the environment. So we'll start out with a few technical details and then move into some more vignettes and examples of how substances might be interacting in the environment. All right, so the first concept we need to get out of the way and learn about is that of the partition coefficient. So a partition coefficient is going to be some measurement that will measure that will describe how a particular chemical might be soluble between two different phases of solution. So from water to air, between two different densities of liquid, as it moves from one soil type to another. So any two different substances that a chemical might be moving between, the partition coefficient will help to describe that. One of the main partition coefficients that gets used a lot is this log KOW. So log KOW is going to provide some measurement, some indication of how hydrophobic or how lipophilic, because those two things mean the same thing, a particular substance might be. KOW gets defined by how a particular substance will organize itself between two different liquids, particularly water and octanol. So the OW in KOW stands for octanol and water. So it's the partition coefficient between octanol and water. So octanol, this is an 8 carbon length thing. This is octanol. And as you look at this compound, so this, when you get a whole bunch of octanol together, it exists as a liquid. So as you look at that molecule octanol, does it look like it's going to be terribly polar or non-polar? Which way do we think it's going to trend? So it does have an OH on one end, but otherwise it's just a string of hydrocarbons. So does that suggest polarity or non-polarity? Non-polarity. All right, so we have octanol, and I've drawn octanol here as this kind of dark blue. So octanol is going to be non-polar. And so what kinds of chemicals do you think are going to want to dissolve into this non-polar liquid? Polar or non-polar type substances? Non-polar type substances. So the more non-polar, the more lipophilic or hydrophobic something is, the more of that concentration we would expect to find in the octanol. Versus water, water is where our more polar, our more hydrophilic or lipophobic compounds are going to settle out in the water. So the way in which you would go about doing this is you would get some beaker, fill it up with equal parts water and octanol, add your chemical compound, shake it all up, let everything mix and become homogenized, and then let it separate. And so once it then separates, we can find ourselves with basically 3 general situations. So in this first situation, we've taken our octanol and water, added our chemical compound, shaken it all up, let it all separate out. And here, the chemical compound, these little purple pentagrams here, those are going to be equally distributed. So there's the same amount of concentration of the chemical in the octanol versus the same concentration of the chemical in the water. This would give us a KOW of approximately 1, right? The ratio in octanol is, or the amount in octanol is approximately the same as it is in the water. And when you make that ratio, it comes out to be 1. So this would suggest some compound that has a mix, like a very even mix of both polar and non-polar attributes. So when we look at that molecule, we might expect quite a few hydrocarbons, but also quite a few polar functional groups like nitrogens and sulfurs and hydroxides and all of that jazz. All right. So if it comes out with a KOW of 1, it's really anyone's guess kind of how that's going to go into an organism or into some particular pocket of the environment. When we mix everything all up and we let everything separate, if there is less of that compound in the octanol and more of it in the water, When we do that math of a small number divided by a large number, we end up with a KOW of less than 1. So a KOW of less than 1 is going to suggest that this is a very lipophobic or hydrophilic kind of compound, right? More of it. It likes being in water, so it's hydrophilic. It does not like being in the non-polar substance, so it is lipophobic. So if we have a substance with a comparatively low KOW, less than 1, then we would expect it to travel more through watery pathways, be much more of an environmental concern rather than inside an organism concern. All right, and then last but not least, by process of elimination, I think we can all guess where this last one is going, where more of that concentration is going to be in the octanol, less of it in the water. And so we're going to end up with a KOW of greater than 1. And this will suggest something that is lipophilic, i.e. hydrophobic. It's going to like being in more tissuey types substances, so it's going to be much more of an organismal concern. Those lipid reservoirs that organisms tend to have, or if it's an organism that utilizes wax a lot, so say insects or other invertebrates that have that waxy chitin, or plants that have a waxy cuticle to protect them from dehydration, those kinds of organisms are going to be much more affected by lipophilic kinds of compounds because they utilize way more lipids than others. All right, so those are some general trends. And of course, like everything, these are not kind of absolute rules. And of course, we need to consider compounds relative to each other. So here's a little table from your textbook that demonstrates the various KOWs and solubilities of some common substances. And here they've given you the KOWs of some common pesticides. So we've got malathion. Here, this is the fancy chemical name for a particular form of a polychlorinated biphenyl, a PCB, and then here is the fancy chemical name for the pesticide dioxin. And so we can see that they're all greater than 1. So if they're greater than 1, remind me, does that mean they like being in water or they like being in oil? They like being in oil. So, so these things like being in oil, they like being in fatty things, waxy things, cutically tightening kind of things. All right. So if you were considering the risk to particular organisms that these would be exposed to, so they're all going to like waxy things, but they're all going to go into those waxy things to a greater or lesser extent relative to one another. So even though everything is above 1 here, we are less concerned. I'm not saying we're not concerned, but we are less concerned about malathion in this instance and much more concerned about dioxin being found in those fatty tissuey sorts of organisms because it has that higher KOW. So it's even more lipophilic than this is. So they're all lipophilic, but this one is even much more lipophilic than this one. Does that make sense? Okay. There's lots of other measurements that we can consider about where things are going to go. One I want to touch on briefly is vapor pressure because it is here. So vapor pressure, this is going to help us think about the likelihood of transition from or between different substance phases, right? Like matter exists in 3 phases, gas, liquid, solid, and vapor pressure gives us an indication of how easily that substance is going to move between gas, liquid, and solid phases. So the higher, so the lower the pressure, the less likely it is to transition between those phases. So these are pretty low pressures. So again, kind of relative, and because they're really, really small numbers. So the lower the pressure, we're not so worried about it moving between phases. So this dioxin has the lowest amount of vapor pressure here. So this is the one that we're the least concerned about it changing form on us, right? So if it's distributed as a liquid, we know it's going to stay as a liquid. We don't have to worry about it sort of instantly vaporizing. Like if you've been in, say, microbiome lab and you have to clean off your bench and you hose it down with alcohol, wipe the alcohol, and then that alcohol just kind of evaporates. That's a high vapor pressure. It doesn't take a whole lot of effort for that alcohol that you sprayed down on your microbiome bench to go from the liquid that you sprayed to just air evaporating. So this really low vapor pressure suggests that it's not likely to move. Things that are going to increase the vapor pressure and increase that likelihood of transition from liquid to gas kind of transition is temperature. So if we spray dioxin outside when it's really, really hot, we're going to increase this number and increase the ease with which dioxin is going to transition from a liquid to a gaseous phase. Just like water is going to evaporate more quickly hot outside versus when it's cold outside, same thing is going to happen here with all of these. And we can get a sense of how easily that's going to happen by looking at that vapor pressure. All right, all good? Okay. All right, so, excuse me, stability and recalcitrance. So we also want to be able to describe chemicals in terms of how long they're going to stick around and how easy they are going to be to move between things. Just because something is lipophilic doesn't mean it's going to get into that lipid space within an organism easily. So we want to think about residence time. So residence time is going to give us a sense of how long that chemical will exist in a particular environment before being acted upon by something. So when we think about residence time, we're thinking about substances, like just how long a substance will persist. So for example, if we remember back to the pyrethroid compounds. So the pyrethroid compounds, naturally derived compounds, they break down pretty readily with exposure to ultraviolet light. So those compounds are going to have a short residence time as long as we consider their exposure to ultraviolet light. So the residence time can be short based on the presence of something like ultraviolet light. Other things like the like larger compounds, the ethynyl estradiol, for example, that can potentially have a very long residence time because there's not a whole lot of things that are going to break it down very easily. It doesn't break down with ultraviolet. If it's in a watery habitat, the kind of wave action doesn't break those molecules apart very easily. And so once something like ethynyl estradiol gets into an environment, it's going to stick around because it's harder to break down. And so it will have a longer residence time. So residence time is one thing that we can consider. When substances have a long residence time and resist some sort of degradation or resist being moved from one form or location to another, we can consider that particular compound recalcitrant. So recalcitrance is kind of a verb form of calcium. So the calc here is not actually calc, it's calc, as in calcium. And when you think about calcium, right, we usually think about bones, and our bones usually stick around for a pretty long time. So recalcitrant substances are going to have long residence times, and they'll stick around. The opposite of recalcitrant is a term called labile. Labile has its root in able, right? So it's able to move, it easily moves. And just like labile just kind of rolls off the tongue, these substances are going to easily move from one pocket of the environment to another. They will transition from one form to another fairly easily. So we can be concerned with chemical substances being either recalcitrant with a long residence time or labile with short residence time. We can apply these ideas of residence time, recalcitrance, and labileness to things other than toxins, and they actually get their start in non-toxic things. We'll see next week the application of the term residence time to pure water. We can think about the residence time of pure water. If we talked about other more important substances in the context of, say, environmental chemistry or mineralogy class, we would be talking about recalcitrant and labile in terms of substances that organisms need to survive rather than substances that they don't want to acquire at all. So these terms are fairly flexible in their application, but we're going to consider them here in the context of chemicals that we don't want in our environment. All right, everybody good? Okay. Additionally, in addition to residence time, we are going to be dealing with two very similar sounding words, adsorbed and absorbed. So adsorbed is when molecules stick to a surface. So one of the things that one of the topics of interest that say Dr. Montross. So Dr. Montross, the organic and inorganic chemistry, biochemistry, her bailiwick of organic chemistry is she designs particular coatings that have different properties to attach different kinds of molecules to them. And so she's got research students currently looking at designing different coatings that could interact with, say, glyphosate from Roundup weed killer, or PFAS from ski wax, and looking at how you can maybe design these different coatings to be stickier for things like glyphosate or PFAS, that you can help clean those substances out of the environment. And so what she is trying to do is she is trying to design these coatings so that they adsorb those particular compounds better than nothing, or other things that aren't doing things quite as well. So when we talk about substances being adsorbed, we're talking about adding those particular molecules of chemical to some surface or to some other thing. So when you spray yourself with DEET before you go out for a hike, you are hoping that those DEET molecules will adsorb to your skin and not just fall off, so that the DEET actually does the job of protecting you from mosquitoes. As opposed to absorbed. So absorbed is when we are mixing one solution with another. We are trying to get two solutions to be one. So for example, our water and octanol mixture, those two solutions will not absorb each other, right? You can mix them up, but ultimately they will separate. If you have an oil and vinegar based salad dressing, you can shake that up so that you get an equal distribution. But if you leave that bottle sitting, you get a separation of that oil and vinegar. Those two solutions do not absorb each other. But something like if you take acid and mix it into water and you give it a good stir, those two solutions eventually become one. Those two solutions have absorbed each other. So absorbing refers to almost a homogenization of two substances. So when we think about things being absorbed, we're usually thinking of the chemical being sort of homogenized and evenly distributed within some solution, usually bodily fluids or whatever the fluid of the environment is. So as you are reading various literature papers and they use the word adsorbed versus absorbed, now you have a sense of where to go with those terms. All right, so there's our technical details out of the way. And so now we can kind of move to some larger scale concepts about how things are going to move through the environment. This dog just loves walking around campus. It's like the fourth time I've seen this dog walk around campus. Oh, there's always time for a dog. Okay, so we're here in the environment. The environment generally consists of three main regions. We have the land, where we all are. We have the atmosphere that we're all breathing and interacting with, and then we have the water, which also interacts with the atmosphere and everything else. So when we think about the distribution of environmental contaminants within the environment, we usually start by sort of saying this chemical has contaminated the water, or this chemical has contaminated the land, or one of the three pockets. However, all of these pockets all interact with each other. You know, we're here on the terrestrial phase, but we have to breathe the water, or breathe the air, and we have to drink the water. We don't breathe the water and drink the air, other way around. We have to breathe the atmosphere and we have to drink the water. So we here on land are going to be interacting with those two pockets. So anything that happens here on land is also going to affect that atmosphere and that water. Very similarly, anything that happens in the atmosphere ultimately affects the land and the water, because what happens in the atmosphere will deposit itself on the land and on the water. And for most things, water is kind of the last stop. Water usually collects in downslope sorts of places, right? Like where you don't get puddles on hilltops, you get puddles in valleys. So everything usually runs downhill water. And so we think of water as kind of the final destination for lots of these things. But water can, in fact, interact with land and the atmosphere. Things evaporate from the water and go into the atmosphere. Water levels can rise and go onto land. So as we're thinking about any of these contaminants, it's important not to pigeonhole them into one particular component of the environment, because that particular component of the environment can interact with all the others. And there was a recent paper that came out. You know I love my recent papers. So this recent study, this is out of the University of Delaware, and this study was looking at the contamination of rice and spinach. And they particularly looked at rice and spinach because these are two really common sources of food for babies, right? Like rice pudding and those bananas and rice and like all the little baby jars and cream spinach and all that good stuff. These are really common baby foods. And so they wanted to look at the contamination of these particular crops with various metals. And they wanted to look at flooding of those fields as a source of those metals. So they looked at rice and spinach fields that experienced flooding from downstream places. And they looked specifically at the deposition of arsenic and cadmium, lead, mercury, and also arsenic. This particular graph that I've selected here from the paper shows arsenic. So if you go to the study, you can see all of their graphs. I just sort of picked one. But what they did, so they looked at these fields experiencing different amounts of flooding. So all of their graphs are kind of organized in the same way, where they have flooded fields, and then they have some different levels of flooding, and then finally, non-flooded. And you can see that there's a pretty significant difference in the concentration of, say, arsenic in one of these is spinach and one of these is rice, and I forget which one is which. But it almost doesn't matter because the flooded field has a really high level of arsenic in both these cases compared to the non-flooded that has very low levels of that arsenic in both cases. So when this was consistent throughout all of the metals that they looked at, including cadmium, lead, and mercury, metalloid arsenic, there's the word arsenic before. So this is just some text that I took from the press release about the article. And then here is the article itself if you wanted to read much more about it. So what happens, even though things sort of end up as their final destination in the water, that water can get its, sort of have its sequel by flooding and recontaminating land. And I imagine that we will be hearing a little bit more about this in the coming days because the Louisiana Gulf Coast, words in the right order, is currently experiencing a hurricane. There's a hurricane that's hit Louisiana right now. It might be moving its way into Alabama finally. But so it's bringing lots of torrential rain. One of the patterns that we've been seeing with hurricanes in the last 10 years is that lower grades of hurricane bring much more amounts of rain than do higher grades of hurricane. So like with a category 4 or 5, you're much more worried about that wind shear damage. With category 1s and 2s, you're much more worried about that flooding because it's just dumping a shit ton of rain on you. Not that there won't be massive amounts of flooding with a category 4 or 5, but that flooding is coming mostly from storm surge rather than from rain deposition. So we've got a category 1 in Louisiana right now, dumping a lot of rain. And so we're going to be hearing all about the consequences of that flooding in the next couple of days as they start to clean up. All right, so we do need to be concerned about how things are going to be moving through these different pockets of the environment. And we even have a way to mathematically describe how things are going to move through the different pockets of the environment, how likely things are to move from atmosphere to soil to water, etc. And that, so we can think about different ways of moving. Let's see, so we can think about things moving through different systems from a thermodynamic perspective. And when we think about things from a thermodynamic perspective, we're sort of looking at the final end state when everything is in equilibrium. And so when things are in equilibrium, this typically happens with enclosed systems where you have two adjacent things that cannot interact with other pockets. So let's say, for example, like something like a reservoir. It's not exactly a perfectly closed system, but it's as close to a closed system as we might get. Reservoir levels are controlled very tightly. The way that things get in and out of a reservoir is about as managed as you can get. So a reservoir might be something like a closed system. And when things are at equilibrium, that's when that KOW is going to come into place. And we'll think about, what the distribution of that particular compound of interest is between the watery component and maybe the organismal component. We can think about the actual movement through time of a particular chemical and focus on the kinetic. And so we're more worried about thinking about things in a kinetic way in terms of open systems. So the rest of the world, not highly controlled reservoirs or wastewater treatment plants. And the way in which we're going to kind of help navigate our transition from totally open to totally closed in any given situation is going to be this term called fugacity. Here's a fun word. I'm probably not saying it right, but this is how I'm going to say it. I'm going to say it fugacity. I'm sure there's a better way to pronounce it. So fugacity is going to help us describe the tendency of a pollutant, of a chemical, to move from one phase. And when we say phase, we again here mean solid, liquid, gas, or compartment. And when we say compartment, we mean air, water, land. So fugacity kind of encompasses the whole ability to move thing. How is it moving? Where is it moving? It's going to get all of it. And so fugacity encompasses both the kinetic and the thermodynamic, because we consider not only, it helps us describe not only how likely and kind of help us to measure that movement through time, but it also helps us get to when it's finally at equilibrium and everything is done and set, and everything is said and done. So using fugacity, we can get a sense of the thermodynamic properties of something, because when we have the same fugacity in all phases, that will suggest to us that equilibrium has been reached and we are now in a closed system. So this is not something that I will actually have you calculate. Rather, we're just going to kind of think about this term F fugacity and what it means. If you were to calculate fugacity, you would want the concentration of your particular chemical. And then Z here, this describes, this is what's called the capacity constant. And that capacity constant describes how hard it is to cross a particular boundary. How hard is it to go from solid to liquid? How hard is it to go from air to soil? How difficult is that? And that's going to be a number that is different in almost every situation. So really, we're just going to conceptually think about, all right, if you have some fugacity value, how would you compare that? And what can it tell you about things? Yes. Mm-hmm. So this particular form, right, so this particular formula goes with that statement. So when you have, so you will know that you're at equilibrium when the fugacity of your chemical in one place is equal to the fugacity of that same chemical in a different place. Does that make sense? So this is the formula that would describe this sentence right here. All right, so formulas are all well and good, but pictures and diagrams are better. So here we have a environment. And I realize that this doesn't look like an environment. So what we have here is we have some water, we have some biota, we have some soil, we have some air, we have some moles. And this diagram is great, but again, it's not particularly intuitive as an environment. So let me redraw this diagram as an environment. So first, we are going to have a lake. So here we have a lake, the water. And that water will be interacting with some soil. I can extend this bank up here, right? So we've got some soil. And in that soil will be some biota, or maybe even a little fishy. With our biota. That lake will further be interacting with some sediments, the bottom of the lake, sediments. Last but not least, we'll have some air, purple clouds, because why not? All right, so here is our environment that this diagram is depicting. Does everyone see that this diagram now shows an environment? All right, so now that I've translated this diagram into the real world, we can think about what is actually happening in this diagram. So in this diagram, we have two chemical compounds, sulfatep and chlorophenopsis. And so this is represented by S and C, and we're looking at in the water, and we're just going to imagine that we're in a boat in the middle of the lake, and we've just got two beakers full of this stuff, and we just poured it in the lake. For science. All right, so we poured our stuff in the lake, and this diagram is showing us basically at time 0. This is time 0. And so at time 0, we've just poured this stuff in the lake. And so the concentration of this stuff in the rest of the environment is 0. It's not in the air yet, it's not in the soil, it's not in the organisms, it's not in the sediments. Is everybody with me so far? Okay, so this is time 0. This next diagram is the same habitat, but sometime later. Sometime later. At this point, we don't really care how much time later, just later. And so now we have concentrations of these two compounds in all of our different habitats. And so now we can start to think about the fugacity differences between these two different compounds. So if we go just back here, so the fugacity is the tendency of that pollutant to escape or move to one phase or compartment. So we're thinking about how likely is some chemical, and we're going to think about this in terms of very likely or not likely. All right, so here's our time later environment. So when we look back at the water and we think about how much has migrated out of the water to other pockets, the ability of things to migrate out of the water to other pockets between these two chemicals is about the same, because the concentrations here are not that different, 75 versus 77. It's not that different. So things are able to leave the water comparatively about the same. So now the question is, where is it easiest for each of these chemicals to go? And which one are we going to be more concerned about in whichever pocket? So when we look at the organisms, biota, the concentration of these compounds is again about the same, and it's comparatively low. So in terms of the ease of moving from water to biota, not very fugacic. It's not easy for these things to move. The same is true going to the soil. The concentrations are higher, but they're about the same. So both of these compounds have a little bit higher fugacity moving from water to soil, but we're not more worried about one over the other in that case. Similarly for the sediments, soil and sediments are pretty similar. So we can think about these two pockets very similar. Last but not least, we've got the air. So here in the air, we have now wildly different concentrations. The Sulfotep is much higher in the air than the chlorophenopsis, chlorophenvinphos, however the hell you say that. And so the fugacity difference now between these two compounds is the Sulfotep has a much higher fugacity because it is able to move much more easily from the water to the air than the chlorophenopsis. So in terms of ease of movement, the Sulfotep is generally going to have a higher fugacity because not only can it move to all of these other compartments at least as easily as C, but it's going to move into the air much more easily. So it will have a higher fugacity. And that's about the level that we're going to think about this. We're not going to actually worry about calculating this. We just want to sort of look at some results and be able to describe them using that term. Does that make sense? Yeah. All right. So there's our, so this is our general chemical model. Okay, everybody good? All right. So let's think about how we get things into the air. We'll start with the atmospheric pocket and then worry about the other. So typically when we are adding pollutants to the atmosphere, they are going to be either as gases or really small particles, really, really, really small particles. Depending on where you are in the earth, we can do a little bit of predicting about how those chemicals are going to move, where they're going to go, how they're going to be distributed. We have all of these really well-known models for how air moves in our atmosphere at different points on the globe. So generally speaking, the closer you are to the equator, you have these Hadley cells that describe the movement of air in, so vertically, so from this loop right here, this shows how air is going to move from the ground to the top of the atmosphere. And so from the ground to the top of the atmosphere, these Hadley cells go. In the north, they go counterclockwise, and in the south, they go clockwise. But from the equator, so from the equator, air goes up, and then it goes north or south, depending on if you are north or south of the equator. Everyone with me? Okay, so once we've gone up, then north or south, depending on if we are north or south of the equator, all of the air then also horizontally moves westward. So air moves from east to west. And you can see this demonstrated because it's hurricane season. And so we can watch hurricanes. We can watch hurricanes form off the west coast of Africa and move this way. So Hurricane Francine, that's the one that's hitting Louisiana currently. We've been watching Hurricane Francine since it was a cloud formation coming off of West Africa. We watched it move across the central Atlantic and then finally organize itself into a hurricane right about here. We've been watching it all this way. All right, so we have these regular currents here, and then as you get a little bit farther north, a little bit farther south, basically all of that reverses. So now in the north, the air is going to rotate to south or to north. Horizontally, it's going to move east. And we see that again with our hurricanes. They demonstrate that for us nicely. So that hurricane will come up over Louisiana, where it then gets picked up by these east direction winds and moves out back into the Atlantic. So whenever you're watching those hurricane tracks, I'm sorry, I'm a nerd. I love watching the Weather Channel. I have since I was a little kid. If there weren't so much math and weather, I would have been a meteorologist like Dr. Attard. But so we can see that hook over South Central US. And if you watch hurricanes, if you get into like nerdy hurricane weather news, you'll watch that hook all the time. We're seeing it all the time. And that's because as hurricanes get driven east to west by these westerly winds. They come up over the US and then they get picked up by these winds blowing west to east and get blown back out over the Atlantic. We see it all the time. Okay, so we have these very regular air movements that we know where they're going. We know approximately how fast. We know how hard they're blowing. We know all this stuff about the atmosphere. So when there is a pollution event in the atmosphere, we can predict where those things are going to go. When particles get diffused, or sorry, when gas contaminants get into the air, it will diffuse. So those contaminant particles as gases will be evenly distributed with our air molecules, nitrogen, etc. Particulate contaminant will go some distance, but then depending on how large it is, it will ultimately settle out. One of the things that helps particulate contamination settle out faster is rain or snow. So this is one of those. So if you are a pollen allergy sufferer, when are your pollen allergies the least annoying? Right after it rains, right? You get that nice rainstorm, it washes all the pollen out of the air, and then you go, I only needed my inhaler once today, right? Because the pollen gets washed out of the air. Maybe when you were a kid, you heard growing up, don't eat the first snowfall. If your parents ever told you don't eat the first snowfall, it's because that first snowfall is going to have all of the summer driving particulate contamination in it coming out in that first snowfall. You don't want to eat the first snowfall. Give it like 2 or 3 snowfalls before you eat it. All right. So how do things get into the atmosphere? Things are going to get into the atmosphere primarily from combustion. So we get a lot of inputs coming from combustion. And when we talk about combustion, we're mainly thinking about fossil fuels, but also wildfires. There's currently quite a lot of wildfires going on in the West. And there was a Buffalo National Weather Service office. I wish I'd grabbed their little infographic that they always show. But they had a post this morning on their social media about how in the next couple days we can expect some effects from the wildfires in the West. So we are going to see the particulate effects of the wildfires in Southern California coming our way in the next couple days. And so our skies will be maybe a little bit milkier, a little bit hazier. You might have noticed already this morning, if you were up with the sunrise like I was, then you probably noticed that brilliant red sunrise. And you'll probably notice a brilliant red sunset tonight. That's all. The redder the sunset, that means there's more wildfire smoke particulates coming into our atmosphere. So wildfires can add these particulates. We'll talk more about wildfire particulates. I've got a whole couple of weeks or a whole week blocked off for it. Fossil fuels, obviously. Those fossil fuels are going to release greenhouse gases like carbon dioxide. The combustion of greenhouse gases is not our only source of these greenhouse gases. One really prominent source of greenhouse gases is actually cows, cattle, whether they're dairy cows or whether they are beef cows, it doesn't matter. But cows can emit quite a lot of methane. And we're worried about methane as a greenhouse gas because methane has a much higher ability to retain solar heat energy than carbon dioxide does. And so cows, when they fart, they release quite a lot of methane. It's the methane that makes farts smell. And so one of the sort of big areas of agricultural science right now is trying to figure out how to make cows less farty, less gassy. So there's a lot of research going on in various places. Cornell is doing quite a bit of this research. The way that we figure this out, you might be wondering, how the hell do we know how much methane is coming out of a cow? So here's a cow that is all kitted up to measure said methane. So here's the sensor reading thing, and they've got sort of a little thing on their nose to capture those gases that it's exhaling. And it's also got a sensor installed, kind of like the red thermometer, a little bit, to measure how much is coming out the other end. The cow is fine. The cow is still able to eat and pass gas and do all the things that cows do normally. They are not very bothered by this equipment. And so we're able to measure how much methane is coming out. And one of the things that we are finding is that if you If you can add a little bit of seaweed, just a little bit of nori, just a little bit of Sarracenia, not Sarracenia. I've forgotten the name of the sugar seaweed, the sugar kelp that we often use. You can take that, dry it up, grind it up a little bit, mix it into their feed, and it actually really significantly reduces the amount of methane, like knocks it down something like 70%. Just a little bit of seaweed is able to knock down the amount of methane. It's crazy. So they're still kind of figuring out why the seaweed does that, so that we can figure out other ways to get that effect without maybe necessarily using seaweed, although seaweed is a great way of doing that. And I'm happy to talk at length about why later. Don't have time now. There's so many cool things that seaweed does. But so there's those greenhouse gases that we are concerned about. We are also concerned about combustion residue, combustion materials interacting in our atmosphere to create acid rain. So I introduced the idea of the nitrogen oxides and sulfur oxides, the NOx and SOx. So this is a quick little diagram showing how the NOx and SOx contribute to the creation of acid rain, helping to form either nitric acid or sulfuric acid as part of our rain. And we're worried about acid rain in our atmosphere because that rain eventually falls on land and on water, and it does a lot of damage. One very visible way that acid rain has done a lot of damage is with this geologic formation right here. So this geologic formation right here, this was known as the Old Man in the Mountain. This was a very famous geologic feature in the state of New Hampshire. If you can find a New Hampshire quarter, you know how the quarters have like all the states and things on them. If you can find a New Hampshire quarter, this is the image that New Hampshire chose for its quarter. And when that quarter was made, this thing was still there. And it was like 2 years later, the whole thing collapsed. And it collapsed due to acid rain. So the acid rain eroded this rock such that it fell off. And so here's the remaining cliff face, with the Old Man in the Mountain superimposed over where it was. So this rock face is no longer there. The thing that is on the New Hampshire state quarter is no longer in existence because of acid rain. In the Adirondacks, Adirondack lakes were very severely affected by acid rain for a really long time. The pH of some of those lakes had dropped to something like 4 in a lot of places. There were no fish, there were no plant life in a lot of lakes in the Adirondacks, and through decades of work by various groups in New York State to reduce the nitrogen and sulfur component of greenhouse gas emissions, those lakes have been rehabilitated and they are now much more healthy. They have fish and plant life in them again. And if you have vacationed in the Adirondacks recently, you probably haven't heard too much about, oh, don't go to that lake, it's pretty acidic. Whereas opposed in the 80s and early 90s, you did used to hear about those concerns. Let's see, other components that we are worried about getting into the atmosphere include ozone and smog. So ozone, chemical formula for ozone is O3. And ozone is a complex substance because when it exists in the stratosphere, ozone is good. We like ozone. Ozone is good in the stratosphere. In the stratosphere, ozone helps protect us from ultraviolet radiation. However, when ozone is created down here where we are in the troposphere, ozone can combine with other particulates to form smog. So smog is a word that means smoke and fog together, and it is ozone combining with other particulates. So here we see a city both without and with smog. This is, I want to say this is Beijing. So this is Beijing on a good air day versus a bad air day. This is looking out at the same vista on a good air day versus a bad air day. Ozone and smog in the troposphere are created through a combination of fossil fuel emissions, smoke, and other particulates. Here on the east coast of the United States, we have not been that concerned about ozone and smog in our cities. This is primarily due to the way in which our general directional winds blow. Remember, we're in the part of the globe where the winds are generally flowing west to east. And so all of our East Coast cities, the winds blow from west to east. So any smog that forms in New York City, in Philadelphia, and Boston, Washington, D.C., pretty much immediately just gets blown right out to sea, and it doesn't stay in the city. On the West Coast, again, we're flowing west to east. And so any smog that gets created in LA, Portland, Seattle, the wind is blowing from the ocean into land. And on the West Coast, not only do we have that wind blowing from the ocean onto land, pushing all of our smog back onto us, but on the West Coast, we've got some mountains that run right up the middle of California into Oregon and Washington, the Cascade Mountains, and those mountains stop the wind at the very low levels. And so all of that smog gets trapped over the city. When I was growing up in Southern California, where I was going to college, I lived right up against those mountains in Southern California. And so all the smog from LA, San Diego, all of the rest of the Inland Empire got blown to where I was going to college, and it just got trapped there. And I had never had like chronic asthma or bronchitis ever in my life until I went to college. And then every year I was in college, I had chronic asthma and bronchitis. One year, there was one semester that it was so bad that I got asked to leave class because I was coughing so much. That I had bronchitis so bad. I was regularly drinking. My usual go-to was tea with as much honey as I could stand and like 3 or 4 cough drops dissolved in it, because that was the only way I could get through class without disturbing people. So it gets bad on the West Coast. And so a lot of the emission rules that we have come to us because of all of the efforts that it took to clean up West Coast air to the point where it was livable. So here you only have to, here in New York, you only have to get your car inspected every 2 years for smog. Over on the West Coast, you got to get it inspected every year. And it's California is one of the largest car consuming states, drives emission standards for a lot of vehicles. There was a scandal about a decade ago with Volkswagen, where Volkswagen had installed these cheater devices in a lot of their cars that were meant to trick California emission detection machines. So when you got your car inspected, these cheat devices would send false clean signals to the inspection machine. And Volkswagen got found out, they got sued out the ass. And there's still financial fallout is happening from that smog detection, or from those smog cheater machines in Volkswagen. So ozone at lower levels can be bad. Let's see, so we're mainly concerned about ozone and the smog problems that it can bring when it's in the troposphere. Again, when ozone is in the stratosphere, where it's supposed to be, where we're not, it's good. The only problem is that we have other emissions in our atmosphere that break down that ozone layer in the stratosphere. And those compounds that break down ozone in the stratosphere are called chlorofluorocarbons, or CFCs for short. So CFCs. So chlorofluorocarbons, these are compounds that were primarily found in flame retardants and also primarily found in coolants. So we currently don't make these compounds anymore, but back in the day, your refrigerator ran on CFC, your air conditioner ran on CFC. I have very distinct memories of being a kid. My dad was a mechanic, and we grew up we were living in the desert. It was really, really hot. And so one of the things that we would get hired to do a lot was to recharge people's air conditioners. So we would go down to the auto store and we would buy cans of Freon. You just buy a can of Freon at Napa Auto. And there was this kind of stethoscope looking thing that you would hook the hose end up to the air conditioner. And then it would go to this kind of scissory sort of end, and there were spikes in the handles of the scissors, and you would clamp those spikes into the can of Freon. And then you had to shake the can of Freon to get the Freon out of the can, into the spikes, into the tube, into the air conditioner. And it was a really great thing to do to give a 5-year-old something to do to burn off all that 5-year-old energy. Here, shake this can for 20 minutes. So that was my job when I was a kid, helping my dad, was to shake cans of Freon. And it was nice because it's, it's 115 degrees out. That can gets nice and icy cold, and you can hold on to it and have nice cold hands and your health and dad. But yeah, that was all CFCs. So, so those CFCs would get released into the atmosphere, and they would get swept up by air currents into the stratosphere. Once they were in the stratosphere, UV radiation would hit these CFC compounds. And these CFC compounds would start to break apart in that ultraviolet radiation. Namely, it would release the chlorines that were attached to that carbon. The chlorine, the free chlorine, would then run into some ozone. That chlorine would then break apart this ozone, creating a chlorine oxide and then just a free regular oxygen. And then the more chlorines were being released, the more you would break up that O2 into chlorine oxide. And so it was just this cascade of CFCs being released into the atmosphere, being broken apart by ultraviolet radiation and destroying molecules of ozone. And so we started to get these really big holes in our ozone layer, forming primarily over the Antarctic. They were forming primarily in the Antarctic because these compounds were distributed globally, but then what would happen is during the Antarctic spring, as the snow would melt, the CFCs that had settled out during the winter would be sort of revolatilized. And so you had this sort of extra concentration dosing happening in the Antarctic as winter CFCs would be revolatilized in the spring and summer, go back into the atmosphere and break apart even more ozone. So we started to see that ozone hole really significantly over the Antarctic. And it got to be so bad that in 1987, literally the whole world got together in Montreal and collectively agreed over the course of like 2 weeks, like imagine the UN actually accomplishing something. Like we hear about the UN in the news, and they make speeches and they say things, and then everything goes about as it was. The world is still terrible. There's still wars. People are still starving. Nothing actually happens. Imagine if the UN actually accomplished something. That's what happened in Montreal in 1987. The UN actually did something. So there was an international summit, and over the course of like 2 weeks, the whole world agreed, yeah, we got to stop making these CFCs. And they stopped making CFCs. They stopped exporting them. They stopped putting them in things. And today we are seeing actual regeneration of ozone in the stratosphere. It's been slow, but it's happened. And so whenever I'll come back, but here is the image. So this is what our ozone used to look like. Here's the hole in the ozone. So the darker the blue, the less ozone there is. So this is the hole in 1987. There were still, so even after we agreed, there was still sort of latent CFCs. Like we'd made all this stuff and we're like, well, we're not just going to destroy it, throw it away. We still got to use it. But it was slowly tapering off. And now finally, this is, almost 10 years old now, but we're starting to get some closure and some reconstitution of our ozone. So whenever folks get really despondent about things like climate change, we try to hold on to the hope of 1987 in Montreal. Like we did it before, we can do it again. We just got to find, something that everyone can glom onto as, yeah, this is a problem, we got to do something. We haven't quite hit on what that next thing is yet that we can all get behind, but I'm sure we'll find it eventually. It is possible. We did it before, we can do it again. All right, everybody good here? Okay, there's my bit of hope. All right, back to this. So similarly, we can follow radioactive fallout through all these processes as well. So just as an example of the kind of particle distribution that we can get with our atmosphere, here's first of all a good example. This is dust or sand being blown off of the Sahara Desert, right? So here's the west coast of Africa. Here's the edge of the Sahara Desert. And those atmospheric winds pick up the sand and the dust from the Sahara. And just like the hurricanes, they blow it east to west. And you might be thinking, dust, that's not good. But this dust is good. This is the dust that is going to provide really important nutrients for phytoplankton and zooplankton in the Atlantic Ocean that's going to do things like feed krill, that's going to feed whales so that we can have baby whales and dolphins. This is very good dust. This is very good dust. The same atmospheric movement that guides this dust can be used to track things like radiation fallout. So here, for example, I really wish I'd made this map bigger. So this was one of the map tools that we use to track potential radiation fallout from the 2011 Fukushima nuclear reactor meltdown following the tsunami and earthquake that happened in 2011. So even though it happened kind of a world away in Japan, not too many days later, that radiation was being found on the west coast of the US. But we knew it was coming, and so we could take steps to mitigate that and to protect things from it. And we were able to track that because we know how the atmosphere. So we can use our knowledge for both good things and to protect us from harm. But I want you to remember these kind of things when you hear certain individuals ask, why can't we nuke hurricanes? And this is a legit question that somebody has asked. Somebody important has asked this question on camera before a lot of people. Yeah, this is. I would hope that after this, you would understand the answer to why we can't nuke hurricanes. I'll just leave that there. Okay. So now that we know that there are all these things in the atmosphere, we do, how do we know that all these things are there? Especially carbon dioxide. Carbon dioxide is a really important compound. And we're just sort of doing almost a quick little introduction to climate change here. But we've set ourselves a number of goals regarding carbon dioxide over the years as an environmental pollutant. So in 1992, we had the really nice goal to reduce to 1990 levels by the year 2000. We tried, we didn't. In Paris, this was when we had the idea that we really needed to limit our carbon dioxide to, we need to limit our carbon dioxide inputs to the atmosphere in such a way as we incurred no more than a 2 degrees Celsius increase in global average temperature. We're still under that 2-degree limit. We're still under this 2-degree limit. We are not under the 1.5 degree limit. So as of last year, we did pass the 1.5 degree global average increase in temperature. And again, this is over pre-industrial levels. Why do you think we set this level of pre-industrial? Like what does it mean to be pre-industrial? Does anyone know what it means to be pre-industrial? What does it mean to be pre-industrial? Yeah, so yeah. So it was in the Industrial Revolution when we figured out, hey, if we burn this coal stuff, we can drive machines and make steam and all that jazz. And so it was in the Industrial Revolution that we started burning coal, a fossil fuel, and then all the other fossil fuels followed therefrom. So that's why we aim for that. And so that pre-industrial level is 1870-ish, 1870, 1880-ish, somewhere in there. It was a time when we had thermometers, we knew what the temperature was. We had records for various things. So that's why we set that level of pre-industrial is always the benchmark that we're comparing things to. Yeah, so if you want to read more about where we are currently, here's a nice, easy news article about that. And I do plan on talking about this a little bit more, so I don't want to give the same lecture twice. All right, so things can move all throughout the atmosphere, but occasionally things get kind of stuck, right? The wind isn't always blowing just as hard equally at all the times. Occasionally, things get kind of stagnant in our atmosphere. And this is when particular pollutants can become toxic. Our normal course of action especially for atmospheric pollutants is to think that dilution is the solution. This used to be a very common phrase back in the 60s and 70s, that if we just dilute things enough, it won't be an issue. And that is how a lot of our emissions were treated. And so one of the things that we did because of that is we built these smokestacks for these emissions, and we built them very, very tall so that they would be caught by the wind and just get blown away before it was a problem, right? Spread it out, dilute it. However, when the wind isn't blowing, those smokestacks, they put it up and then it just sort of comes right back down. And that's when we start to get these local events of thresholds being exceeded for particular pollutants. And this leads, when things become localized, this leads to compartmentalization. So compartmentalization is when some toxic pollutant becomes hyper concentrated in a very particular way. So one example that was happening, so these examples right here, this is Sudbury in England, and this was a nickel smelting manufacturing plant. And so concentrations of nickel, of oxidized nickel, were coming up in the smokestack and then sort of depositing over this area of London, or not London, England, Sudbury, England, and contaminating folks there. So locally, these individuals had higher concentrations of nickel in their system than did folks around them. And just as another example of some compartmentalization that can happen, here's a quick little study looking at cadmium and zinc in some bivalves, and looking at those effects there. Again, we'll talk a little bit more about this when we get to our wildfire section, but here's another incidence of localization. If you've wondered what wildfire smoke looks like from space, this is from 2017. These are fires in Canada. And here are those smoke plumes staying localized over the area where that fire is burning. So those individuals there are being exposed to a higher rate of exposure to particulates and other contaminants that are in that wildfire smoke than, say, folks over here, because that smoke is just sort of sitting there. All right. And all right, so that kind of concludes our atmospheric portion of this. Any questions about generally the atmosphere before we move on? Yes. Mm-hmm. 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 Maybe. I mean, yeah, I mean, yeah, I mean, learning about all this stuff definitely makes you not want to like go out in nature, because like shit, all this stuff is out there. So I think there's almost two things kind of going on there, because one, there is the increased exposure to things like pesticides, wildfire smoke, other contaminants that can harm immune systems and other physiology. Conversely, there is at the same time going on an increased, and I know medical science kind of goes back and forth on whether or not this is really a thing, but for lack of a better term and a lack of my expertise in this exactly, I'll use the phrase the hygiene hypothesis, where like, so when I was a kid helping my dad in the garage, our version of fun was to see who could get their hands covered in the most brake grease, and then the way you cleaned that off was with gasoline, and then you were ready to go to lunch. As opposed to now, that horrifies you all. As in the 80s, that was course de rigueur. But now that is horrific, right? Like, my niece and nephew, when they were little kids, they would go out to play and their mother would be like immediately washing their hands and wiping them off with antibacterial wipes. And those things just did not exist when I was a kid. So at the same time that there's this increased level of toxicity that is happening in the environment around us, there is simultaneously alongside it going on an increase in cleanliness. And there are a lot of folks that put a lot of stock in the idea that that increase in cleanliness has reduced our exposure to pathogens, and that that reduced exposure to pathogens is what leads to an increased rate of various allergens. And I don't know enough about the topic to say much more about it other than that's what their hypothesis, if that makes sense. So I think those two things are going in parallel, or you might be thinking that they're going in parallel. But as to, is wildfire smoke causing peanut allergies? Not so much, if that makes sense. Does that answer your question? All right. Yeah, did my best. Any other atmospheric kind of questions? Okay. All right, we'll try to blitz through these last few slides here. So we can now move on to land and water. So there are several sources of contamination that we want to think about when we're talking about land and water. We can think about landfills as a source of contamination. We can think about fertilizers as a source of contamination, various chemical sprays. Things that end up in soils can be transferred up through the food chain, through food webs, is what we mean by trophic transfer. Substances can get washed downhill to water bodies. Excuse me, and things can get re-aerosolized back into the air. So as images of that are meant to kind of encapsulate all this, here we have, this is a landfill in Africa where folks are going through that trash and they are scouring for metal components to recycle them. So a lot of our old electronics get shipped over to places like Africa. And then folks in Africa will cull through all of that material to separate out the metallic components and try to recycle and sell those metallic components. And that exposes a lot of people directly to things like cadmium, lithium, all of the heavy metals that go into like circuit boards, batteries, that kind of thing. Here we've got a crop dusting plane. So one of the main ways that we apply pesticides to crop is through these crop dusters. These are planes with nozzles and you load them up with pesticides, they fly, zoom low over the crop and release that substance. We still use crop dusting planes. Crop dusters often seem like something anachronistic, like you would see it in The Wizard of Oz or other black and white movies about the Great Depression. But we do still use crop dusters. They fly over our agricultural fields here in Western New York all the time. And here, this is a mountain. This is in Southern California, not too far from where I went to school. And there was a fire here. So you can tell that there was a fire because it burned right here. And all this pink stuff all around it, this is fire retardant. So planes will come up with buckets full of fire retardant and they'll drop it on the surrounding forest to prevent it from burning. And so you'll see mountains with all of these pink and orange dustings on them like they went to Holi. And they've got all of this color all over them, but it's really fire retardant. And it'll be there for months until eventually it rains enough that it all washes off. All right, so amongst the land and water sectors, we're worried about how long things are going to last in there. Different compounds are going to last different amounts of times. Metals are among the longest lasting compounds, and they don't break down. And if you remember what we talked about with metals earlier, they're elemental. Metals are elemental. They do not change anymore. They're not a string of hydrocarbons that you can break apart into different substances. A metal is a metal. So we can again think about the residence time of those metals. We can think about for some metals how, whether it's a recalcitrant metal versus a labile metal. Is it soluble in water? Does it need something else to be soluble? Is it in wet soil versus dry soil? How easily will it move from water to soil, soil to water, air to either of those components? And if it's something like a radioactive component, then we want to be concerned with its half-life. How long should that, or how long does that metal need to be in the environment before it is not any different from background or becomes part of the background? Even when radioactive substances decay and don't become any radioactively different from background, that radioactive decay often is the only way you do get a different metal transition. And that metal transition isn't from metal to something non-metal, it's from one metal form to another metal form. So there is still no breakdown of those metals. As we think more about persistence, one of the big factors about land that can affect the persistence of particular chemicals is what kind of soil is in that land. The different kinds of soils can hold things differently. So when we think about how do we describe what kind of soil there is a way to do that. So the way that we describe the different kinds of soils that exist is with this lovely little diagram right here. This is our soil pyramid. And this soil pyramid describes for us the proportion of inorganic components in our soil. So when we think about the inorganic components of soil, there are three main kinds of soil, or three main kinds of inorganic components: clay, silt, and sand. And when we think about those inorganic components, we're mainly concerned with how easily water flows through them. So sand is the largest inorganic component of that soil. And so when we think about water flowing through sandy soils, water flows through pretty easily. Sand are pretty big pieces and the water just kind of goes straight through. If you've ever gone to the beach, right, the waves wash up, they hit the sand, and then as soon as the wave is gone, the sand is nearly dry, comparatively dry. So we see that water flows through sand very, very easily. Silt and clay get progressively smaller. And so as you have progressively smaller pieces, we make the pathway that water has to travel through those particles, between those particles, longer, because there's more twists and turns and curves that the water has to navigate with those smaller particles. So sand retains the least water, silt retains a bit more, and finally clay holds on to the most, right? If you've taken a ceramics class or a pottery class, that clay, you get that nice clay and you squeeze it in your hands, and what happens? Water just oozes out of it because that clay is holding on to so much water. In addition to the size of the inorganic particle, we also want to think about how much organic is also part of that soil. The soil isn't just inorganic, it is also some organic bits, decomposed plants, animals, detritus, things of that nature. So you can almost imagine kind of a fourth axis coming down through this pyramid, where we can start with basically like 0 organic to lots of organic. And so anytime on this soil pyramid, you start to see the word loam come into play. As soon as we start to see loam, that means a very high organic content. So loamy soil is mostly organic, very little inorganic, mostly organic. The higher the organic components, the more the more of the chemical compounds we've been talking about are going to be retained by that organic component, right? Because organic components are going to have all sorts of functional groups stuck all over them: hydroxides, nitrogen, sulfurs, etc. They're going to be very, very sticky to all sorts of different compounds. They'll also have lots of non-polar plasma membranes breaking apart. They're going to be interacting with the non-polar kinds of compounds that we've been talking about. The greater the organic component of the soil, the more of these kinds of compounds will be retained. So when you mix things like organic with clay, you get a really high retention rate of those particular organic compounds. And we didn't quite get everything finished that I wanted to talk about because it is time. So we will end it there and pick up with the next slide next week on Tuesday. And we'll be finished here for the day. And go Bills. Done for next class besides textbook reading. If you haven't met with your group members and exchanged information yet, I would do that. If you haven't looked at the preliminary methods for our experiment yet, I'd do that because we're going to start doing that next week too. All right, get out of here. Have a good weekend.